Hello, and welcome to this tour of the Couchbase connectors for Kafka and Elasticsearch. In this talk, I'll cover why you might want to use the connectors, we'll talk about how they work, and then we'll show how to set them up. My name is David Nault. I'm a software developer at Couchbase working on the connectors. In my personal time, I maintain a library for accessing java.comments at runtime, which you should totally Google. All right, so let's get started with a refresher on how Couchbase stores and replicates your data. A Couchbase bucket is partitioned and replicated. Each bucket has 1024 partitions, and a document's key determines which partition it gets stored in. The partitions are distributed among the nodes of the Couchbase server cluster, and each node is responsible for a different set of the partitions. These partitions are independent of one another. Each partition has its own history of the document changes within that partition. The connectors tap into these change histories and propagate the document changes to an external system. So let's look at the protocol that the connectors use to listen to the document changes. This protocol is called DCP, or the Database Change Protocol. DCP is a low-level binary protocol. It's engineered primarily to support data replication within a Couchbase cluster or between clusters in different data centers. So a DCP client opens a connection to a Couchbase node and then tells it which bucket partitions to stream data from. There's one logical stream for each partition, but multiple streams can be multiplexed over a single TCP/IP connection. Each database change event in a DCP stream is tagged with a sequence number, which is it's effectively an offset into the data stream. The DCP client is responsible for remembering the sequence number of the last event that it processed, so that when it reconnects, so when a client opens a stream, it can tell the server which point in the change history to resume streaming from. Of course, as you can imagine, a large Couchbase cluster might generate a tremendous amount of database changes. So in order to handle the massive flow of data, you can distribute the DCP clients and have each client stream from a unique subset of the 1024 partitions. So that's a quick look at DCP. Now let's take a look at Kafka. Here's a quick intro for people who haven't worked with Apache Kafka before. The Kafka is essentially a message queue with support for stream processing. The topics are write-only with a configurable message retention policy. Like a Couchbase bucket, a Kafka topic is partitioned and replicated. Kafka is open source with enterprise support provided by Confluent Inc. They contribute to the Apache Kafka development, and they have a Kafka distribution that includes a management front end and other advanced features. Kafka has a plugin framework called Kafka Connect for getting data into and out of Kafka topics using off-the-shelf connectors. Instead of writing code, you can build data processing pipelines by configuring connectors. The Connect framework defines two main component types. You have your sources on the left there and your sinks on the right. A source generates data for publication to a topic, and a sink consumes records from a topic and processes them in some way. And often this means writing them to a data store. There's a third component type called a single message transform, or SMT for short, which can be applied to either a source or a sink to transform the record in some way before it's published or consumed. The Couchbase connector for Kafka is a plugin for the Kafka Connect framework. It provides both a source and a sink for Couchbase. The sink connector consumes records from a Kafka topic and writes them to Couchbase as JSON documents using the Couchbase Java SDK. This can be useful if you want to replicate or migrate data from an external system to Couchbase. Maybe you want to use the Couchbase analytics service to analyze them in Couchbase. Or you just want to get your data into Couchbase so you can access it there. Alternatively, the sync can run in a mode where it updates a specific field of one or more Couchbase documents based on the contents of a Kafka record. This is a way to let existing Kafka-aware systems modify Couchbase documents without directly using the Couchbase SDK. The source connector uses the DCP protocol we just talked about, and it publishes every database or every document change notification to a Kafka topic. These notifications contain the full contents of the Couchbase document. If you want, you can also include the document's metadata like the source partition, the compare and swap value, and the expiry timestamp of the document. Once the documents are in Kafka, you can send them to a different data store or process the event stream using tools in the Kafka ecosystem. Let's take another look at DCP for a moment. This protocol was designed to support replication. This has certain implications for what it can and cannot guarantee in the context of the connectors. Within a single partition, the order between two notifications is the same as the order between the writes that generated the notifications. So we can say that the protocol guarantees ordering within a partition. However, since Couchbase partitions are independent of one another, it is not possible to guarantee the order of notifications that were triggered by writes in two different partitions. This is something to keep in mind. One of the trade-offs in the design of DCP is that there's no guarantee that every version of a document will be represented in the event stream. The server may deduplicate any change, combining multiple changes to a document into a single event. As a result, only the latest version of the document is guaranteed to be delivered. Speaking of delivery guarantees, all the connectors guarantee at least once delivery. The event stream may rewind and be replayed when the stream is reestablished after a restart. The extent of this rewinding depends on a couple factors, like whether the connector previously had an opportunity to save the stream offsets gracefully when it was shut down. And in the worst case, let's start with the best case. Talk about best case first, right? In the best case, the stream will resume exactly where it left off. In the worst case, if the connector is disconnected and stopped for an extended period of time, Couchbase server may restart the stream from the beginning of history, send everything all over again. The event stream may also rewind when a Couchbase node fails over, which brings us to phantom delivery. So to give the very best performance, Couchbase server sends DCP notifications as soon as a change is processed in memory. This happens before the change is sent to the replicas or persisted to disk. When a replica is promoted after a failover, it might not have the most recent changes from the primary instance of the partition. These missing changes are said to have been rolled back. Because the connectors don't have a way of retracting the rolled back changes, this can result in the sync having a version of a document that does not match what's in Couchbase. If this happens, it's as if the connector has delivered a phantom change that doesn't reflect reality. Some systems can tolerate this discrepancy, but for others, that's just not acceptable. So to prevent this phantom delivery, the connectors use a technique called persistence polling. And what this means is that they are periodically asking all the replicas which events they've persisted to disk. And they do this because an event that has been persisted to disk on all of the replicas is unlikely to be rolled back. So the connector then buffers events until persistence polling indicates that it's safe to publish the event. All right, with that, let's dive in and we'll take a look at the Kafka connector in action. Let's start by going to the Kafka connector's project page on GitHub. So I'm just going to Google GitHub, Couchbase, Kafka. There it is, Kafka Connect Couchbase. The connector is open source, released under the Apache 2 license. I'm going to click on this download link down here. So this will take us to the documentation on the Couchbase site in the release notes tab. You scroll down a bit, there's the most recent version. I'm going to copy this link and then do the rest over in the terminal. I'd like to show you how you might automate this process. So I'm going to use curl to download the connector. There it is. And next, I'm going to install it in Confluent. The connector is compatible with a plain Apache Kafka distribution, but for today's demo, I'm going to use Confluent with the Confluent Hub tool for a quick and easy install. Let's do a non-interactive installation. Great. So this implicitly confirmed acceptance of the license. It unzipped the connector and put all the files here. And then it updated the Kafka Connect config files to make sure that the installed connector is in the plugin path. Now that the connector is installed, we can start up Confluent. I'm going to spin up just a local dev environment for Confluent using the Confluent local start command. I'm not going to spin up the entire Confluent stack. I'm just going to start the Connect service and the services it depends on, like Zookeeper and Kafka. This will take a while, so we'll fast forward this part. Great. So the Kafka Connect web service is running. Let's take a look at the logs of that service. Confluent local log connect, and then this is the little incantation to tail it. There it is. So when we start the connector, we should see some activity over there on the right. Okay, now I'm going to go back to this top left terminal window and unzip this connector distribution archive because it contains some sample config files that we're going to use today. They're config files for the source and the sink, and there's two versions of each file. There's one for that's just a Java properties file and one that's a JSON file. Today we're going to show how to configure and run the connectors using the REST interface to the Connect service, and for that we'll use the JSON files. Start by editing this config file for the source connector. This is where you'd do things like set your Couchbase credentials. This is going to work just fine for me. And you also configure the bucket that you want to stream from. I have the travel sample bucket installed, and we're going to use that one today for the demo. One other thing to take note of here, the topic. This is the Kafka topic that the connector is going to publish the records to. All right, I'll save this file with the changes to the bucket name. The next step is to post that config file to the Kafka Connect web service. And to do that, it's a little fussy. I have an alias set up, a little post JSON alias. I'll show you what that does. it runs curl, does a post request, and sets the content type header to application/JSON. So let's do that. Let's do post JSON, and we're going to send this file. We'll put an @ sign in front so curl knows it should read the post body from that file, and then the address. It's running on localhost port 8083. The path is connectors. Hey, look at all that action over on the right. So that's the log output, and here the poll returns 5 results, 3 results. That's the connector in action, replicating documents from the travel sample bucket in Couchbase to the Kafka topic. Great, that's what we were looking for. So we can verify that those documents are on the topic using another little alias I've got set up here. This uses the Kafka console consumer command, which is included in the Kafka distribution, to watch the records on a topic. The Kafka broker is running on localhost 9092. We're interested in the Kafka record keys, so we're going to say, yeah, print the keys too, please. And then this bit says, show us everything from the beginning. And the topic parameter, we're going to supply that on the command line. Oops. So watch topic, and if you remember, the topic name was test default. All right, we saw a whole bunch of stuff. Each line of output here represents a Kafka record. Let's look at this one. This part is the key of the Kafka record. So let's go look in Couchbase to see. This looks good. So here's Couchbase, here's that travel sample bucket. I'm going to look at the documents in it. I'm going to look for a specific document ID. And yeah, there it is. Here's the document in Couchbase that the connector published to the Kafka topic there. So that's great. That's what we're looking for out of the source connector. The next part of the demo is going to exercise the Couchbase sync connector. And the plan is to take all of those documents in the Kafka topic and write them right back into Couchbase. If that's really what you want to do, if that's your goal, to take the documents from one bucket and write them to another, there are better ways to do that. You could use the eventing service built into Couchbase, would be one way. But we're just having fun today. And so we're going to do that same thing, but with the Kafka sync connector. The sync connector, the target bucket needs to exist already, so we'll create that, and we'll just call it sync. It doesn't need that much memory. There we go. We'll go back over to the terminal, and here's a reminder, here are the example config files. This time we'll look at the sync file. We'll edit that. Here we go. So the topics here, this is the list of topics that it's going to consume, and we'll just read from the test default topic that the source connector wrote all the documents into. And the bucket, this is the destination bucket that the sync is going to write the documents into, and we called our bucket sync, so there it is. And then I'll save this file. Scrolling through my history, and we'll do another post JSON, but this time we'll post the sync config to the Kafka Connect service. And we should see some more action over in the right-hand pane here as the sync starts up. There's some warnings over there because I'm running a weird version of Couchbase, but that's fine for the demo. And all right, so what happened? Let's look at Couchbase. And now all of a sudden our sync bucket has just as many documents as travel sample. And if we look at those documents, it's the same documents that were over in the travel sample bucket. Now the source connector is still running, and any changes that we make to this travel sample bucket should be reflected in the sync. So let's try it. Let's add a document with an ID that's easy to remember. This is the default content. Now over here, this is in the bottom left pane, we can see that the document got written to the Kafka topic with the ID of foo. You can see that the sync bucket has the same document count, and if we look for that specific document, there it is in the sync. Let's try one more thing. We'll go to the travel sample, and go to the documents and look for that foo document again, and let's delete it. You can see down here in the Kafka topic, this null is not a JSON null. This is a Kafka null, indicating that the record has a null value. That's how the deletion is represented. So if we go back over to the sync bucket, the document count matches. Look for foo, and it was deleted from the sync. So that's it for the demo of the Kafka source and sync connectors. If you'd like to try this on your own, highly encourage it. I'm going to go back to this release notes page and the connector documentation. Over on the left down here, there's a quick start tab. And this is a set of instructions that'll walk you through the process of what we did today. It'll show you some alternatives and some advanced features of the connectors. There's a reference for all of the configuration options for the source and the sync. So I'd highly recommend going through that guide and trying it for yourself. Now let's move on to Elasticsearch. Elasticsearch is a popular distributed full-text search engine for JSON documents. In Elasticsearch, documents are organized into different indexes. An index is like a Couchbase bucket, except it can only contain one type of document, where type it refers to the schema of the document. Older versions of Elasticsearch allowed mixing document types, document schemas within an index, but modern versions of Elasticsearch enforce this one type per index restriction. Data stored in Elasticsearch is sharded and replicated. And like Kafka, Elasticsearch is open source. Enterprise support for Elasticsearch is provided by Elastic Inc. Couchbase Server has built-in support for full-text search. Having Elasticsearch in your architecture diagram might be redundant. However, there are good reasons to use both. Couchbase full-text search currently supports 22 human languages, while Elasticsearch supports 35. Elasticsearch has specialized features like percolator queries, which answer the question, which saved queries match this document? So you can present a document and it'll tell you which queries would return it. If your application needs percolator queries or some other advanced features of Elasticsearch, that would be a great reason to use it. The final reason I'd like to highlight is that Elasticsearch might already be an integral component of your architecture. Our professional services team would love to help you replace Elasticsearch with Couchbase, but that's not something that happens overnight. In the meantime, the Couchbase Elasticsearch connector can bridge the two systems. So what does the connector do and how does it work? Just like the Kafka source connector, it uses the DCP protocol to listen for document changes in Couchbase. When a document is modified in Couchbase, the connector writes the new version to an Elasticsearch index. Since an index can only contain one type of document, and a Couchbase bucket can contain any number of types, the connector's configuration defines type definition rules that tell it which Couchbase documents should be written to which Elasticsearch indexes. Each rule has a document ID condition. If a document ID matches the condition, the document is written to the index specified by that rule. Or a rule can also say to ignore documents that match the condition. The rule can compare the document ID against a static prefix or against a regular expression. This regular expression may contain a capturing group that identifies the destination index. Otherwise, the type definition rule specifies a static destination index. These rules are executed in the order they're defined in the config file. And then when a match is found, the rule evaluation stops. So the first match wins. Only the first rule that matches the document has any effect. And then as a consequence of that, Couchbase document can be written to at most one index. The Couchbase Elasticsearch connector is a Java application, and you can run multiple instances of it if you anticipate a large volume of database changes. Each instance will talk to Couchbase using the DCP protocol and stream from a subset of the bucket partitions. For each database change, the connector evaluates the type definition rules looking for a match, then writes the change to Elasticsearch over HTTP using the Elasticsearch high-level REST client. So if you decide to distribute the workload among multiple connector instances, they have to be configured to work together as a group. You do this by specifying the group name property in the config file of each connector instance. This tells the instance which group it belongs to, and then the connector uses this group name to locate the DCP stream offset documents which the connector stores in Couchbase, and we'll look at those in just a little bit. In addition to a group name, the connector instances need to know the total size of the group and their own rank within the group. The connector uses those two pieces of information to determine which Couchbase bucket partitions it is responsible for. So for example, if there are two members in the group, each group should handle half of the partitions. Which half? Well, member number one says that I'm the first member, so I'm going to be responsible for partitions 0 through 511. Member number 2 takes the second half, 512 through 1023. If you decide to add or remove a connector instance, it's necessary to first stop all the instances in the group, reconfigure them with new membership information, and then start them all up again so they don't get confused and step on each other's toes. That might be fine if you have just a few instances and don't need to scale the group dynamically. But for larger deployments, you may wish to run the connector in something called autonomous operations mode. Makes it easier to adapt to cluster membership changes. So in this autonomous operations mode, a connector instance can join or leave an existing group without requiring manual reconfiguration of the existing instances. Instead, the connector instances coordinate their activities with the help of a HashiCorp console cluster. Console is a distributed key value store, if you think of it like etcd or Zookeeper. It has some nice features that make it well suited for this kind of use case. So in addition to distributed locks that the connector uses to implement leader election among the connector instances, console also supports dynamic service discovery. So when you start a new connector instance, it can register itself with console under the given group name. If this group already has members, the leader of the group automatically reassign group membership to all the instances, and they'll recalculate which partitions they're responsible for. Likewise, when you stop a connector instance, or if the machine hosting an instance fails, Console removes it from the service registry, and then the group leader can redistribute the workload among the remaining instances. The members of a connector group store their stream offsets in Couchbase. This is true regardless of whether you run the connector in autonomous operations mode or manually configure the group membership. The DCP protocol uses a separate stream offset for each partition. The connector stores each stream offset separate Couchbase document. So there's a 1024 of these documents, each one storing the offset for a specific partition. By default, these documents are stored in the bucket the connector is replicating from, although you can define, or you can configure the connector to store them in a separate location if you want the connector to have read-only access to the bucket, for example. Each of these documents has an empty body. The offset information is stored in the document's extended attributes, as you can see on the right there. It's just sometimes called xaddrs. And we do this so that the checkpoint documents won't show up in your nickel or full text search query results. We don't want them polluting your results. Collectively, the set of stream offsets for all partitions in a bucket is referred to as a checkpoint. A checkpoint represents the replication state of the connector group as a whole. The Couchbase Elasticsearch connector ships with tools for managing checkpoints. You can clear the current checkpoint, which simply deletes all the stream offset documents from Couchbase. You can catch up, which writes offset documents to Couchbase matching the current state of the database, so that only new changes from that point on are propagated to Elasticsearch. And the current checkpoint can be backed up to a file on the local file system, and you can later use that file to restore the checkpoint. Okay, now let's take a look. Let's see what it does. Let's start by going to the GitHub project page for the Couchbase Elasticsearch connector. So I'll just Google GitHub Couchbase Elasticsearch. There it is. Connector is open source, released under the Apache 2 license. This download link is going to take us to the Couchbase website in the Release Notes tab of the documentation. Here's the latest version. Let's download that one. I'm going to go back to the terminal and download it with curl. Looks like it's downloads complete. And then these next few steps, let's do in the Finder. I'm going to double click to unzip. And there we have it, the Elasticsearch connector home directory. Let's look in the config directory and edit the config file, example connector config. First thing you'll see in here is the group name. We can leave it as example group, but we'll need to remember that. We'll use that for later. For this demo, we're going to deploy the connector in autonomous operations mode. That means we can ignore the group membership config because this will be determined dynamically at runtime. The connector runs an embedded HTTP server where it serves up metrics. I'm going to run multiple instances of the connector on my laptop. So to avoid port conflicts, I'm going to disable the HTTP server. In this Couchbase section, this is where you would plug in your seed node addresses, the addresses of the Couchbase server. And here we go. Here's the bucket we're going to stream from. For today, we're going to stream from the travel sample bucket. Here are the credentials for Couchbase. You'll notice that the password is stored in a separate file. And we do this so that if you want, you can set different file system permissions on that file, or in a containerized environment, you can mount it in as a secret. But let's look at that separate config file. It's in here under secrets, Couchbase password. And it's just another TOML file, very simple, with one config property in it. Now, if you want, you can use placeholders in these config files. So if you did something like that, the connector would recognize this as a placeholder, and it would read this environment variable and just do a literal substitution, would replace this with whatever the value of that environment variable is. And you might want to do that if you're building let's say you're building a Docker image and you want to inject the password using an environment variable. That's one way you can do it. But for today, we'll just leave it as password. And going back to the connector config here, what else do we want to look at? Here's the section for Elasticsearch where you would plug in the Elasticsearch hosts. This is something I want to talk to you about. The Elasticsearch doc structure config. By default, the connector will write the documents to Elasticsearch with two top-level fields. One of the top-level fields will be meta, and the value of that field will be an object that has the document's Couchbase metadata, like the CAS, revision, the expiry, things like that. And the other top-level field will be called doc, D-O-C, and that'll have the actual content of the document. This is for backwards compatibility with previous versions of the connector. If you're starting a new deployment and you know you don't need the metadata, you can just delete that, leave this metadata field name blank, and change document content at top level, change that to true. And with this setup, the documents in Elasticsearch will be structured just like the documents in Couchbase. I'm going to skip over some stuff here, and here we are, here with the meat of the config, the type of definitions. So here's where you tell the connector how it should map the documents in Couchbase to the different Elasticsearch indexes, how it should route them, like which index it should route them to. This first rule is a good rule to have. It just says that if the document ID starts with _sync:, then we're going to ignore it, and the connector won't do anything with it at all. And that's because these are Couchbase sync gateway metadata documents. So we can leave that document there. This next type rule, this is saying that if it's an airline document, it starts with airline _, then send it to the airline's index. And this is just in here as just to show you what you can do. You can also route the document to an Elasticsearch ingestion pipeline, but we're not going to do that today, so I'm going to delete that. And you can also, this rule is showing how you can use a regular expression to do the match. I want to do something really fancy though. I'll show you something fancy today, and that's using a regular expression with a capturing group to determine the index. So all of the documents in this travel sample bucket, the document ID is prefixed with the type. So you have like airport _ whatever, landmark _ whatever. When your document IDs are structured like that, what you can do is you can say that the first part of the document ID is going to be the index name. And then you have your delimiter. So for the travel sample bucket, the delimiter is an _. And then everything else matches. So what this means is that this will index all the documents as long as they have an _ in the document ID. And everything before the _ will be the Elasticsearch index name. That covers just about everything, so I'm going to delete all the other type definition rules here and save that config file. Now we're almost ready to run the connector. There's just one more thing. We need to start Elasticsearch. I have an alias set up here to run Elasticsearch from a Docker image, so I'll get that started. And back in the top left, while Elasticsearch is starting up, we'll go into the connector home directory, and we'll look inside the bin directory. We're going to run the connector in autonomous operations mode, so that means we're going to only going to use this command right here, the cbes console. Oh, that also reminds me, we need to get console running. So I'm going to run console in development mode on my laptop. It's really easy to run in dev mode. A production deployment is there's a little more management overhead, but for today, the dev server is really easy to get running. And we can actually look at that. We can look at the console web UI. It's running on localhost port 8500, and there it is. The first step to running the connector in autonomous operations mode is uploading the config file to console. So I'll just run this cbes console command, and it should show us some help information and show us all the subcommands. And the one we're interested in today is configure. You do that, it'll show you some more help. It'll show you what the options to the configure command are. Because we're just running console locally and with the default config, we don't care about those options, but we do need to tell it which config file to run or to upload. So I'm going to say input file is the config, the example connector that we just edited. There it is. We saw a little blip over there in the console log as that document got uploaded. And if we look in the UI, in the key value service in console, we can see there is now a config document at this path, and this should look pretty familiar. This is the config document that we were just editing. So let's run the cbes console command, and what we want to do now is do run, and we'll see what are the options there. Now you'll notice we don't need to tell it a config file, but we do need to tell it which group it's going to join. So what it's going to do is it's going to look in console under that directory with that group name and then get the config from there. This other option, the service ID, this is required if you're running more than one connector instance on a node. So I'm going to specify that too because it's just for this demo, I'm going to run 2 different service IDs. Okay. Group, example group, service ID first. And here we go. The connector is running. It's detected it's the only one running, so it's going to handle all of the partitions itself. See Elasticsearch over on the top right, creating those indexes and updating the type definition mapping. Okay, so the connector is pushing the documents through over to Elasticsearch. Let's take a look in Elasticsearch, just verify that the documents are there. I'm going to do that using a Google Chrome add-on called Elasticsearch Head. This is not as fancy as something like Kibana, but if you just want to poke around at the documents, it does the job. Click on the browser tab here, and then we can see, there we go. There are all the different document types. And we can see that the airlines got replicated to the airline index. Click on the landmark index, we can see there are landmarks in there. Click on one of these, we can see the content of the document. So the source right here, that's what we indexed. And just real quickly, we can go over to Couchbase. Here's the travel sample bucket, documents. I'm going to look at that one specific document. And there we go. There's the document in Couchbase on the right, and then an Elasticsearch on the left. And they're the same. That's good. You may have noticed as we were flipping through here, I'm going to remove this filter so we can see all the documents. We can see that there are a bunch of checkpoint documents in the travel sample bucket that weren't there before. These all start with the same prefix, _connector. This number is the partition that the document is for. So this is the checkpoint for the stream offset for partition 0. And this bit at the end is just, it doesn't mean anything, but this is just a little synthetic suffix that forces this document ID to get mapped to this partition. So that, for example, The checkpoint document for partition 1001 gets written to partition 1001. And if we just click on one of these, you can see this has things like the vbucket UUID, sequence number, that's like the stream offset, and then some other metadata the connector uses for maintaining its point in the DCP stream. So that's great. Because we are running in autonomous operations mode, go back over here to the terminal, it's really easy to add a new connector worker, and I'll show you how to do that right now. And we can do this without even stopping the existing worker. So CBS console, run, we're going to start another one. Group, example group, and service ID, we'll call this one second. Okay, so this first node up here in the top left, notice something happened. So it's going to rebalance the membership here. And now you can see that instead of streaming from 1024, each of these workers is streaming from 512. So the leader has distributed the workload. I'm going to go over to console real quick and click on the services tab. So we can see there's a service defined here that's the name of our connector group. Click on it, we can see there's the first one, there's the second one. Those are the names that we assigned with the service ID. And if you click on there, you can see that each one is passing its health check. Now over here, what I'm going to do just to show you what happens, I'm going to go in the top left window here that was the leader, the first connector that we started, and I'm going to hit Control-C to kill it. And now the one on the bottom notices that it's all alone and says, oh, hey, I better pick up the slack for all of those. And if we go back in console, we can see that the console knows that the first service is down. So there you have it. If you want, we can start it back up again. We can just run it again. Membership gets rebalanced again, and over in console, we can see that the notice is back. That wraps up the demo of the Couchbase Elasticsearch connector in autonomous operations mode. I'm going to take one last look at the documentation here. So this is the release notes page where we downloaded the connector. Over here, there's also a getting started guide that walks you through some of the steps we did today. In this guide, we'll show you how to run the connector in manual mode. That's something we didn't do. We did autonomous operations mode. And this documentation also describes all the configuration options in pretty good detail. So I hope you'll try this for yourself and let us know how it goes. Thank you for joining me on this tour of the Couchbase connectors for Kafka and Elasticsearch. If you'd like to get in touch after today, the best way is to post on the Couchbase forum in either the Elasticsearch or the Kafka category.